Welcome to the AI Research Roundup. I'm Alex. Today we are looking at a paper from the Hugging Face trending list, published on December 21st, 2025, which was published about 11 days ago. It introduces CosineGate, a dynamic routing method for residual networks that skips redundant residual blocks using a simple cosine incompatibility signal, and it reaches 91.3% accuracy with 28.5% flop savings on CIFAR 10. The paper is titled CosineGate, Semantic Dynamic Routing via Cosine Incompatibility in Residual Networks. And, as we will see later, the key idea is surprisingly geometric, but it translates into very practical compute savings. Also, the authors shared a GitHub repo to go with CosineGate, and it is pretty lightweight. Right now it mainly includes a single Jupyter notebook, CosineGate, IPYNB, plus a basic README so listeners can inspect the core implementation and run through the method in a notebook workflow. Figure 1 explains why the method can skip work without labels, because it checks whether a residual block adds a new direction in feature space. The diagram shows x as the identity path and f of x as the residual update, with the angle theta capturing how different they are. The cosine incompatibility ratio equals 1 minus cosine of theta, so small angles mean redundancy. The gate g then shrinks or keeps f of x and y equals x plus g times f of x. Figure 2 makes the skip decision feel almost obvious. It says to run a residual block only when it changes direction in feature space. A residual update is the added vector f of x, and cosine incompatibility means 1 minus the cosine of the angle between x and f of x. The left panel shows x and f of x aligned, so the block mostly rescales and can be skipped. The right panel shows an orthogonal update, so it creates a genuinely new direction and should be computed. Table 2 turns that geometric skip signal into concrete accuracy versus compute trade-offs on CIFAR 10. This table summarizes the full comparison, with baselines on top and cosine gate variance below. The ResNet 20 row anchors the no skipping case, so the flops ratio stays at 1. The balanced cosine gate setting matches the ResNet 20 accuracy at epoch 160 while using a smaller flops ratio, which implies a sizable skip rate. Figure 9 shows how CosineGate trades accuracy for computation, so you can pick an operating point instead of always running full ResNet 20. The left panel plots test accuracy against flops ratio at epoch 160, and the key idea is that lower flops ratio means more skipping. ResNet 20 sits at full compute, while CosineGate Ultra and Tuned move left into lower compute with varying accuracy. The right panel reframes that trade-off as peak accuracy versus peak skip percent, which highlights how performance shifts as skipping gets more aggressive. Alright, 2 takeaways stand out. CosineGate turns a simple geometric Q, cosine incompatibility between the identity features and the residual update, into per-sample skipping that is trainable end-to-end. It also shows you can hit practical efficiency points, like matching ResNet 20 accuracy on CIFAR 10 while cutting about 29% of flops, which is promising for edge deployment. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.